A little more about the periodic table. Where did the periodic table come from? Who came up with arranging them like this? It's really kind of interesting. Dmitri Mendeleev is often considered the father of the modern periodic table. Turns out there was also another guy who kind of discovered it around the same time, but I don't remember his name. Some books talk about him and some books don't, but Mendeleev is the guy we remember. He proposed the periodic law, and one of these days I would really like to study the history of chemistry because it's really pretty fascinating. I just don't have time to do that. But you can imagine they had discovered a lot of different elements, and scientists like to categorize and organize things and look for patterns. So they've got all these different elements, and they're trying to make sense of them. And so Mendeleev was looking for patterns in the elements. And so he started arranging them. And originally he arranged them in order of increasing atomic mass, increasing relative mass. And what he noticed was that certain properties recurred. So he ordered them, like here's, potassium and calcium and all of the known ones, he put them in order, and then he realized, and we come around and rubidium and potassium act the same way when we put them in water, when we react them with oxygen. They have similar properties. So that's how he came to put them in the table. So if we look at the periodic table, the other thing that's really interesting about Mendeleev is when he did this, we did not have all of the elements that we have now. There were a bunch of holes in here. And he left spaces and predicted that elements would be discovered in the future that would fill in those holes. And he even predicted many of their properties, what sorts of compounds they would form with oxygen and what their densities and melting points and various things were. And sure enough, elements were eventually discovered that fit in those holes. It was really, really amazing. The other thing they discovered, though, was that the correct ordering was not the atomic mass, but it was the number of protons. There are a couple of places in the periodic table, and here's one example, between copper and zinc, where the mass does not increase. Copper is 63.55. I'm sorry, that one does. I was off a little bit. It's cobalt and nickel. Cobalt is 58.93, and nickel, which is higher in atomic number, is 58.69. So nickel is actually a little bit less massive than cobalt. And there's one other place, I don't remember off the top of my head where it is. But the ordering of mass wasn't quite right. It was the number of protons. But Mendeleev didn't know about the protons. So the periodic table, I think, is just the coolest, most amazing thing ever. And the more you learn about the periodic table, the more you realize just how amazing it is. The order in the periodic table is mind-boggling. So we're going to learn a little bit about the periodic table. So we should be able to recognize from the periodic table 3 broad categories of elements: metals, nonmetals, and metalloids. A metalloid is something that is like a metal but not. Just like a humanoid robot is kind of like a human, but it's not a human, right? Maybe has arms and legs and walks and talks, but it's not actually human. So a metalloid, those are sometimes called semi-metals. So if we look at the periodic table, this one's color-coded. All these guys over here in the light yellow are metals. And then we've got the nonmetals over here in green. And then there's a stair-step line here, which some periodic tables leave off, and I don't like that. I like the stair-step line. Right along this line is the division between nonmetals and metals. And so it kind of makes sense that these elements here in this transition act kind of like nonmetals and kind of like metals, because they're in the middle there. So from the stair-step line, you should be able to predict whether something's a metal or a nonmetal. So instead of remembering right and left or something like that, just pick an element that you know something about? How about oxygen? I think we're somewhat familiar with oxygen, or even helium, helium balloons. Is helium a metal? No, must be a nonmetal. Okay, then everything on this side of the line is going to be pretty much nonmetal. How about iron? Is iron a metal? Yeah. So the guys on this side are metals. The ones in the middle along the line are the nonmetals. I'm sorry, the metalloids. The exception here is lead. I'm sorry, not lead. Aluminum. Aluminum. We are familiar with aluminum, and aluminum is a metal. But most of the rest of these, if they're touching the stair-step line, they are semi-metals. And here's another exception down here, but we're just never going to do anything with him, so we don't care about him. There's another exception right over here. Is hydrogen a metal? No, it's a nonmetal. Why is hydrogen over here? Well, hydrogen's over here for other reasons. And I like to think of hydrogen as the baby brother of the element family. And the baby brother is the one that gets to break all the rules, right? At our house, the baby brother is the one who gets to stay up and watch Psych with Mom and Dad when everybody else has to go to sleep. But that's because they make him take a nap at daycare, and you can try to put him to bed at 9 o'clock. He's not going to go to sleep till 11 anyway, so we decided, why fight it, right? So that's what hydrogen is like. We're going to find out that he's an exception to a lot of rules. So yeah, he's over here with the metals, but he's not a metal. Any questions? So, metals have some similar properties, and many of these will be pretty familiar to you. They're good conductors of heat and electricity. That's why we use metals to make electrical wires. That's why we use metals for our cookware. It's because they conduct heat well. Metals can be pounded into flat sheets. That's a quality called malleability. We say it's malleable. If you take a piece of metal and you bang on it with a hammer, it will dent, it won't shatter. If you try doing that with rubber or glass, you're going to have different results. Or a giant crystal of salt. It's just going to shatter. But metals can be pounded. They can also be drawn into wires. That's called ductility. Metals are often shiny. They are lustrous. And metals tend to lose electrons when they undergo chemical changes. So metals tend to lose electrons. Now, these are general characteristics. So there are exceptions. It's just like if you're talking about men and women and you start to generalize. Yeah, most of the time it's true, but you can always find someone who's an exception. Examples are iron, magnesium, chromium, sodium, all those guys on the left side of the line except for hydrogen. The nonmetals have properties that vary a lot more. They're not as predictable. The metals, for the most part, are solids at room temperature. The nonmetals, some are solids, others are gases. They tend to be poor conductors of heat and electricity, and they tend to gain electrons. So the metals lose electrons, the nonmetals gain electrons. Examples are oxygen, nitrogen, chlorine, and iodine. The metalloids, these guys are in the middle. They're also called semi-metals, and they have mixed properties. Yes?
Can you repeat the fact that metals have, they lose electrons
And nonmetals gain. Yes. Yeah. Nonmetals gain electrons, metals lose electrons. And we'll talk a lot more about that later. So the metalloids are sometimes called semi-metals or semiconductors. You've probably heard of semiconductors. We live not that far from the Silicon Valley. Silicon is a semiconductor, and it's very important in computer technology. Semiconductors are really, really useful because they have these intermediate properties. So they have intermediate electrical conductivity, and that conductivity can be changed and controlled, and that's why they're useful in computer chips. So probably the most familiar examples are silicon and germanium. Arsenic is another one, and those guys are right on that stair-step line. So, example, Let's classify each of these as a metal, a nonmetal, or a metalloid. What about sulfur? It's a nonmetal. How about chlorine? Nonmetal. How about Ti, titanium? Metal. How about Sb? That's antimony. I didn't hear that. Metalloid, yeah. Because it's right on the line there. So this, again, is the type of a question that could show up on an exam. Now, I could ask you about some of these crazy elements. You just have the element symbol. All you have to do is find it on the table. You don't actually have to know what its name is to answer a question like that. The periodic table is divided into different sections. We just talked about metals and nonmetals. But if you look at its overall shape, you see there's this section over here that sticks up and a section over here that sticks up. And so this is in yellow on your screen there. It looks pink on my computer, but that's my computer's problem. The yellow sections there are called the main group elements. That's the main group of the periodic table. And this part in the middle is the transition. It's a transition from this part to that part. The main group elements are more predictable. We can more easily predict their properties from their position in the periodic table. The transition elements are kind of squirrely, and they're much, much less predictable. So a lot of the things we talk about in this class especially are going to pertain to the main group elements, and they may or may not apply to the transition elements. Then we have groups. There are groups and there are periods. And that's probably coming up in a slide, but oh well, I'm going to write it out here. So groups, or they're also called families, and those are the columns. And so this periodic table is showing us the names of some of the groups in the periodic table. So these have numbers. This is group 1A. The group 1A, those are called the alkali metals. Well, is hydrogen an alkali metal? It's not a metal. He's just sitting there being ornery. But these are the alkali metals. Group 2A, these are the alkaline earth metals. So they have a special name. And then we jump over to this side of the periodic table. Group 7A, these are the halogens, fluorine, chlorine, bromine, iodine, halogens. And the far right column, these are called the noble gases. So group 8A. And they're called groups, well, they're called families because just like people in a family have some common characteristics, elements in a family or group have some similar characteristics. So if we look at group 1A, so these are the elements that are included in the alkali metals. And I think we're going to have, no, that's all they do. It's kind of dumb. The alkali metals are very reactive. This is a picture of what happens if you put sodium in water. Thankfully, that doesn't happen when you put aluminum or iron in water. It doesn't burst into flame. Sodium reacts with water and generates hydrogen gas, and it generates so much heat that the hydrogen gas spontaneously combusts. Yes?
So the hydrogen belongs in which family?
Hydrogen's not really in a family, yeah. In some periodic tables, you'll actually see hydrogen listed in two places on the periodic table. It's sometimes listed over in group 7A because it shares some characteristics with 7A also. Yes?
How is helium obtained?
How is helium obtained? I think, somebody else asked me that and I didn't remember to look it up. I think they just get it out of the air. There's helium in the air and you can concentrate it.
Well, they're stating there's a helium shortage.
Right.
So I was trying to figure out.
Yeah, I think that's why somebody else was interested in it, and the idea that we were talking about was, is helium gradually escaping into outer space? Because it is lighter than air, and so it does go up. And is it actually escaping the atmosphere? I don't know. I
And the
don't
same
know.
with neon, is that too?
Well, the noble gases are called noble gases because they don't make very many compounds. For a long time, they thought they made no compounds. They're always present as an element only. Now we know that there are very few compounds that they do make. But neon is a gas at room temperature, so the only thing I can think of is in the air. Yeah. But shortages can be caused by a number of things. Shortages can be caused by the fact that you don't have the natural resource to obtain anymore, or a shortage can be caused because the technology or the equipment or the factory that does whatever you need is broken. And so sometimes in California there's been, a little bit of a gasoline shortage because one of the refineries caught fire or got shut down for something. And so does that mean that there's not enough crude oil in the world? No, it's just we have a localized shortage. So I need to remind myself to look into that now that 2 students have asked me about it. These are the alkaline earth metals. They also react with water. If you throw calcium metal in water, it'll bubble and fizz. Magnesium is fun to burn, so it makes a really bright light. I'm really not sure what the point of these slides is, honestly, because we can look at the periodic table and see those names. I don't know. But these are the halogens. This is a picture of chlorine gas. It's got kind of a yellowish color, and it's pretty toxic. Iodine is a solid. So fluorine and chlorine are gases. Bromine is a liquid at room temperature, and iodine and astatine are solids at room temperature. Those are the noble gases. A neon light actually does have neon in it. And the helium that you put in a helium balloon is just helium. Okay, so which group or family does each of these things belong to? Lithium. Alkali metal. How about boron? Well, lithium is, I'm just having problems. Alkali metal. That's its family. What group number is it in? 1A. Boron is in which group? 3A. Group 3A doesn't have a special name. How about I? Iodine. That's in group 7A, right? And that has a special name, halogens. And AR is argon. Where's that? That's a noble gas in group 8A. And so we need to know those family names because we sometimes refer to them. We'll say, well, this, the halogens do this, or the noble gases. Let's stop.